This is 6.4 of Algebra. So now we've worked with 3 different methods to solve linear systems: graphing, substitution, and elimination. So I want to point out a couple key reasons why you'd use each of those. So graphing, we're really not going to use graphing a ton, but graphing you can use for if you need a visual display, right? You need a picture of it. Also, it's good for if you want to estimate, right? To get an exact answer out of graphing, you have to fall exactly on the integer that you mark, right? You graph it, and it has to fall on a mark. It has to fall exactly on a cross section. Otherwise, it's not very helpful. So we won't really use graphing a ton. Substitution. If one equation's already solved for it, if it's already x equals something, if it's already y equals something, if it's already equal p equals something, right? If a variable's already solved, then it's really easy to use substitution. Also, some situations, maybe it's really easy to solve for one. Maybe it's 2x plus y equals 10. Right? That's not that hard to solve for the y. So then that'd be a good idea to use substitution. So we kind of fall back on elimination. Elimination is great when the coefficients are the same or are opposites. So if we have 2x plus, how about plus 3y equals 15, and we get 2x minus 4y equals 8, right? These have the same coefficient, right? So I can subtract and just solve it. Or let's say the second one was negative, then I can just add them and solve it, right? But also, if it's just not convenient to graph or use substitution, right? Like if there's not a variable that's alone, graphing, it's easiest to graph when it's in y equals mx plus b, right? So elimination is kind of our fallback. Okay, so when we're thinking about a business, there's this thing called a break-even point. And that's when the money that they spend equals the money that they're making. Or in other words, their expenses are equal to their income. And you can see that point right there. If we're graphing it, that's what it looks like there. You can see where they cross is where the income and the expenses are even. They're not making any money, but they're not losing any money. The white area is where they're losing money, because if you see that red line, the expenses is more than their income. They're spending more money than they're making. And everything in the yellow, which would go on farther to the right, is where they're making money, because the blue line, the income, is higher than the red line, the expenses. So let's try our own problem. A puzzle expert wrote a new Sudoku puzzle book. His initial costs are $864. Binding and packaging each cost 80 cents. Each book costs 80 cents. And the price of the book is $2. So, talking about expenses, we're looking at $864 and 80 cents per book. So let's stick that into an equation. That 864, that's just a one-time thing. So we get y equals 864 plus the 80 cents is per book. So this is where I'm going to do 0.8x. I need to have my x in there. For one book, it costs 80 cents. For 2 books, it costs $1.60. For 3 books, it costs $2.40, right? You're multiplying by however many books. And then our income is just that $2 per book. So we get y equals 2x, right? Because we get $2 for every book. We don't just get $2 once. We get $2 for every book. And then I'm going to solve those. So here's my 2 equations. And I need to decide what's the best way that I could solve these. Well, if you think back to what we said on the last slide about choosing different options, these are already solved for a variable. So substitution would be really easy. So I'm going to take this stuff here, and I'm going to plug it in for the y in the other equation. So I have y equals 864 plus 0.8x, and I'm going to plug in my 2x for my y. So I get 2x is equal to 864 plus 0.8x. And I'm going to solve it. So I'm going to subtract 0.8x from both sides. I get 1.2x is equal to 864. And then I need to divide both sides by 1.2. And I get that x is equal to 720. So he needs to sell 720 books and they'll break even. The amount he spent will be the amount he made. If he sells more than 720, that's when he starts making money from it. Okay. So the zoo has 2 water tanks that are leaking. Tank 1, or one tank, but we'll call this one tank 1, has 10 gallons of water. And it is leaking at a constant rate of 2 gallons per hour. So it's leaking 2 gallons per hour. And then we have a second tank, so I'll call that one tank 2, that holds 6 gallons of water and is leaking at a rate of 4 gallons per hour. And they want to know, when will the tanks have the same amount of water? So we're going to make 2 different equations. Tank 1, so we've started with 10 gallons of water. Okay, and then we're leaking, so that's going to be subtracting 2 gallons per hour. So after 1 hour, that's 2 gallons. After 2 hours, that's 4 gallons. After 3 hours, that's 6 gallons, right? We're multiplying by the number of hours. So 2, and let's use H. Tank 2 starts with 6 gallons of water, and we're losing 4 gallons every hour, so minus 4H. And I want to know after how many hours will they have the same amount of water. So, again, substitution looks like the best option. So, I'm going to take my first equation, and I'm going to take this, the 6 minus 4H, and I'm going to plug it in for Y. So, then I get 6 minus 4H equals 10 minus 2H. So, I'm going to add 4H to both sides. We get that 6 is equal to 10 plus 2H. And when I subtract 10, I get that negative 4 is equal to 2H. I divide by 2 on both sides, and I get that H is equal to negative 2. So, after negative 2 hours, they both have the same amount of water. That doesn't make sense, does it? We can't have negative 2 hours. So this is not a reasonable answer. There's no time in real lifetime, right? I mean, on a graph we could go into negative time, but that doesn't actually make sense in our real life situation. So these tanks never have the same amount of water. Alrighty, so we're going to look at one problem, but I want to explain another situation where you see it, is with wind. Did you know that when you fly from, in their example they use LA and Charlotte, and when you fly, the amount of time it takes to go from LA to Charlotte is different than the amount of time it takes from Charlotte to LA. Because winds flow from the west to the east. So when you're flying from LA to Charlotte, North Carolina, it's going to go faster because you have the wind pushing you, right? Picture like a big fan that's blowing really fast and you're trying to walk into it, right? As you try to walk into it, it's going to be really hard, right? You're going to go slower. But if you're going with the wind, you're going to go quicker. So we also see this kind of situation in a stream. So let's draw ourselves a little stream. Here's our little stream. And let's say the water's flowing this way, okay, to the right. When you go downstream, that's when you're going the same direction. So we would be rowing to the right. and the stream would be going to the right. Okay, if we're going upstream, we're rowing against the current, so we'd be rowing to the left, and the stream is going to the right. So we can set this up. In this situation, the rowing and the stream are working together. So let's use R and S. So R plus S, and we'll call that equals our total. When we're rowing upstream, they're fighting against each other. So we've got R minus S equals T. And our problem says that when you're rowing upstream, you get a speed of 2 miles per hour. So this is R minus S equals 2. And when you're rowing downstream, you have a speed of 5 miles per hour. So R plus S equals 5. So here are my two equations. It looks to me like elimination is going to be our best option. You can use substitution, right? All of our variables in this case have a coefficient of 1, so they're pretty easy to solve for. But I think elimination is going to be our best choice, so I'm going to go with that. So R plus S equals 5, and R minus S equals 2. You could add or you could subtract, right? If I add, my S's will cancel because one's positive, one's negative. If I subtracted, my R's would cancel because they're both positive. I'm going to add. I like to add better. R plus R, remember there's ones in front of those, so 1R plus 1R equals 2R. S plus a negative S is just going to be S minus S, so that turns out to be 0, so that goes away. Equals, and 5 plus 2 is 7. Divide both sides by 2, and we get that R is equal to 3.5 miles per hour. So if there wasn't a stream, let's say you're in a swimming pool or something and you're rowing, you would be able to row 3.5 miles per hour. And then we need to plug in to figure out what the speed of the current is, how fast the stream is going. So I'm going to plug into that first one. R plus S equals 5. So 3.5 plus S equals 5. Subtract 3.5 on both sides. We get that S is equal to 1.5 miles per hour. So the stream is flowing at a rate of 1.5 miles per hour. And there's your homework.